Okay. So, any questions on the processor design? Okay. So, yeah, is this slide visible? Hello?
Yes, sir.
Yeah,
Yes,
good.
sir.
Yeah, right. So, see that in the last 2 weeks, so we discussed about processor, where in that basically we have seen how to design the data path of a processor. It means that various entities, various data path components that are required for execution of some basic instructions, around 10 instructions, which spread over all formats, like all three types of formats of MIPS. And then for controlling those data paths, data path components for execution of these instructions, we have also seen what are the control signals that are required and how they are generated, and what are the inputs that are required for the controller, what are the outputs. So all those things we have discussed. Basically, we have seen this very simplest approach, excuse me, like a single cycle approach, where all data path components are occupied for the entire execution of the instruction. And the other approach, which is efficient one, is the pipeline approach, where the data path components are the data path is split into the various phases or various stages, where the multiple instructions can make use of these stages in a ordered way, so that the efficiency or the performance can be improved. So these are the various aspects we have discussed, and all these things actually we are discussing in view of improving the performance. So basically, there are various ways to view the measure the performance of a system, and the one way to perform the measure the performance is that, like for example, given a program, how fast the program can complete its execution and all. So that is nothing but the CPU time. And we have seen that in the very first chapter itself, the CPU time depends on instruction set architecture and actually the high level language program, whatever the programmer will write for the given application. And afterwards, but those high level language is not interpreted by the actual hardware. So you need to convert, you need to translate the high level language code into machine language code by using the instruction set architecture for the given hardware. And then after that, the CPU time also depends on the hardware also, like the processor, memory and all. So far we discussed about instruction set architecture, how it influences the performance of a system. So we know that as we have seen, because when you compute the CPU time, it depends on the number of instructions per program multiplied by a number of CPU cycles per instruction and multiplied by CPU time. So in that, like the high level language or that means the programmer who writes the code for the given application using one of the high level languages. Then afterwards, the compiler, which used to translate the high level language to machine instructions. So these two will basically influence the number of instructions per program. So and then coming to the number of cycles that are required for execution of the instruction, it depends on the hardware, like the processor, memory, and so on. So that way, in the last class, in the last week, we discussed about a processor. So its design and various aspects of processor and all. So with that, we'll come to know that how effectively we can able to implement using a processor for this instruction set to optimize the performance. So in that context, we discussed about the pipeline approach and so on. So there is another data path component, so which influences the number of instructions, the number of CPU cycles that are required for execution of instruction and the CPU cycle time. So these two are also influenced by The another important component, so it's nothing but a memory. So along with the processor, the memory also will play an equal role, a very important role for the overall performance, because as we already know that the program, whatever is there to be executed by a processor, the entire program will be there, will be present in the memory. So every time for every instruction to execute, so the processor should access the memory, should fetch the instruction, or sometimes it will fetch the data, and then it performs, it carry out its operation and all in ALU, arithmetic logical unit, or some other processing unit. So every time for every instruction to access, or for every data item to access and all, the processor should consult or contact the memory. So therefore, the memory access time, or the memory also play very important role in the performance or the optimization of the overall performance of the computing system and all. And here we'll see that actually here the title, if you look at here, large and fast exploiting the memory hierarchy. It means that we should have, everybody wants that actually the memory should be large enough so that the entire program can be placed properly. And and not only one program, because if you perform the multitasking or system where it's not only one program has to be there, there should be multiple programs has to be present in the memory, and so that all these programs can be executed by a processor in a systematic way, in a time sliced way, or in some other multiplexed way, so that the multiple programs will run concurrently, so that the processor can performance will be improved. And then here, that for that reason, we expect that the memory should be large enough to cater all the programs to present. And another thing is that it should be faster. That means the memory, because for every program, as I mentioned, that the CPU access the memory for fetching the instructions, data, and so on. So therefore, it should be very fast enough so that in one cycle itself, in optimal way, within a cycle itself, we should expect that whatever the instruction, whatever the data we are requested for, should be available to the processor and all. So it should be large and fast, means it's like in the ideal case, we expect that the memory should be large enough, and at the same time, it should be faster to fetch the given data. So before going to the details, so let us just see that it's a very broad perspective of what are the different types of memories that are used in a generic computer system. You can see that all of us are familiar with these details and all. Like we have a static RAM, which is generally used for cache memories, and all the technology that is involved in cache memories are the static RAM. And here the access times, you can see that they are very small, it's order of nanosecond, like 0.5 nanosecond to 2 nanoseconds. And at the same time, the cost per 1 gigabyte for this SRAM technology is very high. So it is the static RAM is very expensive, but it provides you the very minimal access time and all. And so usually the cache memories, whatever or the technology that is used in the cache memory is static RAM. And the dynamic RAM, here the access time is like higher, almost like 100 times over the static RAM. You can see that it's about 0.5 nanosecond, means you can see here there are 50 nanoseconds, right? So it's about order of magnitudes higher access time, and at the same time the cost is much less compared to static RAM. And these dynamic RAMs are usually the primary memory or the main memory, whatever we call. So those things are used by this dynamic RAM technology. And so then the last one is the magnetic disk, where you can see that access time is much higher. You can see it's on terms of milliseconds, whereas the above two are in the order of nanoseconds, but here you can see it's the order of milliseconds. And so it means it's very high, access time is very high compared to the other two technologies. And at the same time, you can see the cost per bit, cost per gigabyte is also very less. It's very economical, cheap, provides larger amounts at a very reasonable prices, but the access time is also very high. Because here the magnetic disk, the access time is very high because here the disk it involves the mechanical components. So therefore, the movement of these mechanical components controlling these things and all, so that takes reasonably more access time compared to these two technologies, which are based on the electronics technology and all, like solid state technology. So, and here the ideal case is that actually we want that a memory should have access time close to or access time similar to the SRAM. And we need the capacity that is offered by the magnetic disk and all. It means that it should be faster, and at the same time, it should provide enough memory, like large amount of space, so that the programs can be reside there. So this is our ideal objective. For that, we cannot use the static RAM, because static RAM, the amounts of memory that is provides, because your the the static RAM here, the size is also a bit more. So you cannot offer the larger sizes at that space, in the space, given space. So therefore, the static RAMs are very expensive, but the size that is offered is limited. It's nowadays actually it is in terms of megabytes of is available at a reasonable prices and all. And the ideal thing is that we need to have a static RAM with a larger capacity. So this we can able to see that in this particular chapter. We'll try to see that how these cache memories are exploited for accessing the entire program by the CPU and all. Because the program size is very huge, it's order of gigabytes sometimes, that depending on the program. But the CPU will access the mostly the cache most of the times, many times, because first try to access the static RAM. If it is not there, then it will go up to it will fetch from its dynamic memory, main memory and all. So basically we make use of these three memories in a hierarchical way, where the static RAM will be placed very close to the processor, and nowadays it's a part of a processor. Within the processor itself, it is integrated. And the dynamic memory will be the separate memory chips, not to be main memory or a physical memory, where the CPU can access up to this point, dynamic memory. It will first access the cache, and if it is not there, then it can able to access up to the main memory. It means that it can fetch from the main memory, place it into the static memory, then that way it used. And if it is not there, up to this part, the static memory, dynamic memory and all, fetching or accessing and also these can be done by using using hardware, it can be carried out. So with that, it will be faster. But in case of magnetic disk, suppose, for example, if you want the CPU access a particular memory reference memory address for an instruction or a data, if it is not available at a static RAM or a dynamic RAM, then it will be there in the magnetic disk. But to fetch that to a dynamic RAM or a static RAM, it requires time. It requires, you see, a sort of milliseconds of time and all. So here the compatibility also, because here they are the mechanical components, here these are the electrical components and all. So therefore, usually the hardware is not used here, which basically we make use of the software, that is operating system, will come into the picture over here to fetch the desired data from a magnetic disk to the dynamic to the primary memory or a static RAM and all. So that way we'll see the details later on, next one after that. And here basically here we use the whatever our ideal objective of faster memory and larger memory, like should access very fast and should have enough amount of memory, so that the performance will be better. So that we can able to achieve, or will try to achieve, by using a concept of principle of known to be principle of locality. So here the idea of principle of locality means, even though the programs may be larger in size, but while accessing, all the time the CPU will access only the limited amount of address space in the program. That program may have 1 gigabyte of size, including a data or whatever. But at any point of a time, the program will be like fetch the instructions or a data only in a very from a limited address space, maybe around kilobytes or maybe tens of kilobytes, hundreds of kilobytes. Only in that during that very limited range of address space, only it access the only small portion of program will be accessed at any point of a time. So that provides the principle of local. That means at any point of a time, at any instance, the mostly the program will hover around very smaller, very limited address space in a program, so that one can able to exploit that using the ideas of like a temporal locality and a spatial locality. So what it means here is that even though the program size is very large, you cannot accommodate in the cache memory because the cache memory offers a size of kilobytes or megabytes, assume that. So, but the program size is much beyond that. So therefore you cannot place the entire program into the memory, right? Into the cache memory. So therefore the program should be there at some place at a lower level hierarchy, maybe in the disk or maybe at a primary memory. But whatever the program requires for its execution at that particular point of a time, so those instructions are the data that should be, you have to make it available at the cache, so that most of the times whatever the program requires at that time, it will be available. We have to make sure that it should be available at a cache memory. It should be available at a faster memory or a memory at a higher level or close to the processor and all. So that how do we do that? So these are the two basic concepts or basic principles that are involved. One is going to be temporal locality. It means that the items or the instructions, whatever items accessed recently are likely to be accessed again soon. It means whatever the instructions the program is accessed, the CPU is accessed, it may be likely to be used. It is the most probably that these which are recently used are required further, or maybe used, or maybe recalled, or maybe re-executed again and again and all. So it's known to be a temporal locality. It means that the most recent instructions will be used again and again. So it's known to be temporal locality. And it will be like you can observe that in a program in the case of instructions in a loop, or otherwise if the variables are declared, then soon after that mostly those variables are rigorously used by the program and all. So these are the like examples where you can see that the temporal locality can be exploited. It means that whatever the instructions that are fetched, so that will be placed in the memory for some amount of time, so that the program will revisit all those things and it will make use of them. Then the other one is spatial locality. It means that spatial locality means suppose the items that are fetched from the that are used recently used, and mostly the items the next to that are very close to that in address space. That is, the following instructions are the previous instructions. They are the most likely to be used accessed again and all. It is nothing because as we know that the way the program execution normally we have seen in the when you're designing the processor and all, like program execute by default, it executes the instructions sequentially, like PC plus 4 keep on fetching the next instruction and then place it into the like a pipeline and all. So that is nothing but the spatial locality. That means the instructions that are close to the recent instruction, they are most likely the instructions are most likely the items that will be required by the CPU to process. So that's not to be spatial locality. So it will be like the sequential instruction access, because the program will be sequence of instructions, and usually the instructions will be executed in sequences in a order, unless if there is any like branch instructions or control instructions and all. Uh, and along with that, not only instructions, even if you see that if you have a data array of data, and suppose you are processing the data, which is, the data is available in array, for example, there are multiple data items, then that data items will be stored in a sequence, right? So in that case also you require the to start processing the data, which is an array data structure, then it keep on fetching the data items from the array from the sequential locations and all. So that way, the temporal locality and spatial locality, they will place a role. So by using these two, exploiting these two, so one can able to manage the limited amount or a small amount of memory which is faster enough, where it can able to provide the data or instructions to the CPU and all. So yeah, this is nothing but the taking the advantage of locality. That's what we discussed and all. So if you see the memory hierarchy can be exploited for doing that, like providing the ideal conditions to the CPU as far as possible. Uh, and that means store everything in the disk because the disk is very cheap, economical, provides a huge amount of space. So the entire whatever the all programs should be available at a disk. And then the next hierarchy, the next level above the disk is the primary memory or the main memory, where the CPU can able to access using a hardware, where the currently recent copy recently accessed items from the disk and place it in a DRAM. DRAM is nothing but physical memory. And the most recently one, whichever is accessed by the CPU, by the processor and all, so they should make it available in the cache memory or the static RAM memory, because as we have seen the static RAM memory, the items can be accessed in a fraction of nanoseconds. That means within a cycle itself, it can able to access and all. So that way, by exploiting the memory hierarchy, placing everything in the lower memory, and then the next higher memory can be used the recently used one, and then the most recently used, most required one has to be placed in the cache memory and all. Okay. Yeah, right. So this is the way the processor, and maybe this can be the cache memory, and this may be the main memory. And here this is some basic terminology which is very intuitive. Like here the processor or you can say that the data that will be transferred or moved across these memories will be viewed as a block of data, and that block maybe contains maybe the multiple words or a single word. Usually a process will access like word by word if the depending upon the processor size and all. If it is a 32-bit processor and all, then access the data or instruction of 32 bits at a time in a clock cycle. If it is 64 bits or 128 bits, accordingly that many words or that much size of the data will be accessed. So, but here the data movement, the data that will be transferred across this memory hierarchy, so that will be generally called as in terms of block. So that block maybe contains either a single word or multiple words. That depends on the buses and the requirement and all. And so if the suppose a processor requests some memory address, it just requested for either for instruction or data. That means if the access data is, suppose whatever the processor is requested, if that access data, if the data is available at a higher level, that is in the cache, then it is immediately passed on to the processor. So then we say that it's a hit. That means whatever the processor has been asked from a memory, so it's available. Either it may be instruction or it may be a data item, whatever. Because we have seen that there are two types of memory will be there separately: instruction cache and instruction memory and a data memory. And while executing the instructions and all, you require sometimes the data maybe from a data memory, or sometimes the instructions are required in a sequence by the instruction memory and all. And whatever the processor is requested at that time, if the data or instruction, if it is available in the memory, in the higher order memory, then we say that's a hit. So here the term the hit ratio means out of number of requested request, how many of them were satisfied. It's nothing but how many times the requested data is available at the top hierarchy or at the cache memory itself. So that indicates the hit ratio and all. Because suppose assuming that if there are 100 requests, out of that 97 times your request is as per your request, the data is available in the higher order memory itself. So the remaining 3 times it's not available. So in that case, here the hit ratio means it's like 97%. Like because the 97 times your requested data is available at the cache itself. So therefore 97 by 100. So that gives you the 97% or 0.97. That's if you normalize to 1. So that way it's a hit ratio. So the other one is nothing but the counterpart of that is known to be miss. So out of number of access by a processor, how many times the data is not present in the higher order memory. So it's known to be miss. So if there is a miss, it means that what happens, that means the requested data is not available. So therefore, whatever the data that is requested, that corresponding block has to be fetched from the lower memory to lower hierarchy to the top memory, copied from lower level, and then it has to be given to the processor and all. So therefore, the miss ratio is nothing but 1 minus hit ratio, obviously, right? And so the time that is required to handle the miss will be like that depends upon the nature of the lower memory and how much access time it requires and how much transfer time it requires. And again, it has to pass on to the processor and all. So all these components together will be the miss penalty. That means if a miss occurs, then how much time it is required to get the desired data to a processor and all. Whereas hit means it's directly within a cycle. The moment the processor is requested, immediately it is in the cycle itself, the desired data will be passed on to a processor. Right? Whereas a miss means actually you have to fetch from its lower level. So that depends on the time where it is available and the technology that is used in the lower memory and the transfer time that depends upon the bus width and bus speed. All these things will matters in case of a miss for handling the miss. And we'll see those things one after another. Yeah, the same thing here. Like as I already mentioned here, some terminology. Hit rate, as I mentioned, the fraction of memory access found in the memory, found in the higher level of memory hierarchy. Yeah, hit time is nothing but to access that block, and then time to determine first of all whether the block is present or not. Then afterwards to access that. And as I mentioned, the miss rate is nothing but it's like 1 minus hit rate. And the the miss penalty or the time that is required to handle the miss will be all these components as I mentioned over here, like time to access the block at a lower level and time to transmit the block from lower level to the corresponding level and time to insert the block into the present level or higher level and time to pass again to the requester. So all these things uh, like these are the additional overhead with the miss rate and all. That's a miss penalty, we can call it as, right? So with this section, we'll try to see that the hit rate should be like as close to as one, or at the same time, or the miss rate should be minimized. And other ways that but it's not we cannot achieve the ideal case, and we'll try to see that the miss rate can be minimized or at the same time the miss penalty can be optimized instead of taking a longer time to handle the miss and all. So if you can able to somehow what are various ways to reduce the miss penalty and all, we'll see those things in the later part. So always we know that actually here the hit time is much smaller compared to the miss penalty or other way like. And yeah, here this is just a diagrammatic illustration that you can see that suppose assuming that you have a cache something like that, different entries, and suppose these are the sequence of references, for example, requested by the CPU. The CPU is requesting address of x1, x2, xn minus 1 and so on. And if all these are present and if it is requested for the next address something like xn, and if it is not present here, then you have to fetch from its lower level and you have to make it available here and all. And when you are dealing with the cache memory, because the CPU generates address and that address it corresponds to physical address. That means that address corresponds to the address related to the main memory. That means wherever that particular instruction that is present in the main memory, so that location address or that particular memory address will be provided by the CPU. Or actually CPU provides some other address, but in the translation you will get that particular address, right? And that address is the actually that is present or that is valid for a physical memory. But here we know that there is a small memory known to be cache memory, which is faster one. So that is close to the processor or that is a part of a processor and all. The processor first check the cache entries. First check the cache memory, whether this particular instruction is or particular data item is available in the cache or not. So here the question is that because the CPU generates always the address, the physical address, but here the data that is actually first checked in the cache is organized differently because the cache size is much smaller compared to the physical memory. So in that case, first of all, how do we know that the data is present in the cache? Or where to check in the cache? Because the cache size, because assuming that the main memory size equals to, for example, order of like 1 gigabyte or 2 gigabytes, for example, 2 GB RAM or 4 GB RAM. That's the size of a main memory as of now currently. Earlier it will be like megabytes, like a 250 MB or like 500 MB and so on. And now it's in terms of gigabytes. And if you look at the cache now, at present, the cache size equals in terms of megabytes. But the actual physical memory is in terms of gigabytes and all. So, like, how do you do the mapping? Because the CPU generated address corresponds to main memory, right? But the actual data, not actual data, but the recent data, most probably it may present in the cache, and the CPU access the cache first because it will fetch the data faster and all. So then how do you do the mapping? Like how does the CPU address with that address, how do you find out directly from the cache whether the data is present or not? So these are the various things that we'll look into now. We'll see that how the, for this, first of all, we have to see that how the cache is organized and what is the relation between the cache entries to the entries or addresses in the main memory. And once if you know that, then you can able to, by using some appropriate mapping, you can able to find out from the CPU generated address itself, you can able to find out whether the item is present in the cache or not. Yeah, we'll see that. Yeah, here. So there is one way of organizing the cache or providing the relation between the cache and the main memory. It's known to be direct mapped cache. So here, if you look at here, just for this example, if you look at here, you see that assuming that the bottom one is the main memory, which contain there are 32 entries are there. That means the main memory holds, assume that there are 32 blocks. It can able to hold. The capacity of a main memory is 32 blocks. And assuming that the cache memory size equals to 1/4 of that, it can hold up to 8 blocks, hold up to 8 blocks. And here there are 32 blocks are there in the main memory. So one way to map these 32 blocks to these cache entries will be one tech that method, direct method is known to be direct mapped cache. So here the idea here is that directly the address of this the main memory, the block address of this main memory will be all these blocks will be have a directly they have a relation to like any if you take any block address, so there will be directly only one entry in the cache that reflect that corresponds to. So it means direct map to cache. It means that for every block in the main memory, there will be only one location. For every each of the block, there will be some specific location in the cache where that block will be present. Where that block will be present. But here the cache size is different from the main memory. It means that a main memory here there are 32 blocks are there. Cache memory only 8 blocks are there. So therefore, you cannot have that means for every block there cannot be have a like a unique cache entry cannot be there, right? Cannot possible because the cache size is much smaller compared to the main memory and all. So therefore, the way here the cache and the main memory they are mapped will be there will be multiple entries in the main memory. So the multiple entries in the main memory are pointed to or like indexed to a single entry in the cache, a single entry in the cache. For example, if you look at here, there are 32 blocks are there, but here there are only space for 8 blocks only. So therefore, what it will do here is that here will manage somehow like for every 4 block, not for like there are in the main memory, there are 4 blocks where all these 4 blocks has to be placed into only one block, only one entry in the cache. It means that there is only one block space, but for this block space, there are 4 entries in the main memory. They will compete for that. And those 4 entries also specified here clearly. Like you can see here. So this one and here this one, here this one, this one. Likewise, if you see the black, the blocks with the blue colored, so all of them has to their place in the cache will be only in this block. It means that only one can exist into that at any point of a time. Only one can exist at any point of a time. So this is known to be direct mapped cache. It means that for every block, there will be only one, there is a single location or a specific location in the cache where that block can present. The block can be placed over here and all. So in that way, so since the block cache size is small, so therefore they will have a multiple blocks in the main memory and their address or their location in the cache will be the same. That will be only one entry will be there. So here in this context here, There are 32 blocks here, 8 blocks, and so therefore, so there are 4 blocks for among these, like 4 blocks have only one cache entry. Like for each of the 4 blocks, they have only one entry in the cache will be there. So how do you this mapping can be done will be in the case of direct map cache. Here, assuming that here the block address varying from 0 to 31, there are 32 block addresses are there, but here cache can accommodate only 8 blocks, 8 blocks. So therefore, we can manage this by using this expression or by using this formulation. You can able to find out the address in the cache. That means if you take a particular block address and then if you ask that where that block is present in the cache means, then by using this one, the block address modulo the number of blocks in the cache. Here the block address will be, here you can see that the block address will be like 0 to 31, that is 5 bits, right? And then the number of blocks that the cache can accommodate is 8. So that means the 3 bits and all, right? The address of the block, or say the index of the block in the cache will be like it can accommodate only 3 bits. So the way we can provide this, the relation or the mapping will be like you take a block address and then you modulo with the number of blocks that are provided by the cache. That gives you the entry in the cache and all. That gives you the entry in the cache. So there are 32 bits over here, and sorry, there are 32 addresses. So here in this, as per this, the cache size equals to 8. So therefore, the block address modulo 8 that provides you the cache entry or cache index or the address of the block in the cache and all. So if you take any one of these, so if you want to know that actually what is the location of this particular block in the cache means, you perform the modulo or take the address, the block address, and perform the modulo with the size of the cache in terms of blocks, then it will give. Or otherwise, indirectly, like if you take whatever the block address is there, so in that block address, the lower order bits, that depending upon the cache, here the cache supports 8. So therefore, the 3 bits, the lower order 3 bits of a block address, so that provides you the index. That means where the cache location, in the particular location, the block may present and all. So that way, from the address itself, if you can able to identify the block address, so from the block address, the lower order bits provides you the cache index. That means where this block, the main block main memory can present in the cache and all, right? So here that way here in this example here, the block address is specified by the 5 bits and the cache can accommodate 8 blocks. So therefore, the lower order 3 bits of each block corresponds to the cache index or the address of a cache where this block can present. So if you see that, for example, this blue colored one, so where if you see all the blue colored blocks here, their lower order bits remain same. The lower order bits remains 101, 101, 101, 101 and all. So this is nothing but you can see that's the reason this block, this blue colored block, the entry in the cache will be like 101, right? So that is because we are performing modulo, so then the modulo will perform 8 by we are doing modulo with 8. So therefore, the lower order 3 bits will be result as a reminder. So that will be the index. That is the position of the cache position where the particular block will be available. Okay. Right. So the next one is that, yeah, we know that the cache index, like the location of a block in the cache. Then after that, how do you check that whether the block is present or not? Because we have seen that there are multiple blocks are mapped to the same location in the cache, right? So just by knowing the index, the block index, we are not aware that actually whether the block, the specified block is present or not, right? So therefore, we need some additional higher order bits that are required to check that whether the desired block is present or not, whether the requested block by the CPU is present or not. For that, in addition to the block address, we also require the higher order bits also, the higher order bits. So here, if you look at here, like here in this case here, this is the block address. And from this block address, actually, if you perform this one, you can come to know the cache entry, right? So the lower order 3 bits indicate the cache entry. So from this lower order bits, actually, we are not aware that whether the desired block is present or not, because the lower order entry will say that, yeah, whether will indicate that the block is present or not, right? But whether that block is the desired block or not, because there are 4 such blocks in the main memory with the same cache entry, right? So for knowing that one, we need to have the remaining higher order bits are required. Those are known to be the tag bits. So if the block is here, this particular block where the tag is 00, and whereas this particular block tag equals 01, 10, 11, and on. So with that, you need to have some additional bits are required in the address space, basically the higher order bits and on. And with that higher order bits, we can check that if the block is present in the cache, whether that block is the valid, whether the block is the desired block or not. So for that purpose, we make use of the higher order bits of the address and all. So that higher order bits are known to be the tag bits and all, known to be the tag bits. We'll see that when you look at the example, then it will be clear to you. So here in this case, for example, if you look at here, this is the example where you can see that. So the address of this is the complete address of the block and all. And so from this address of the block, actually, when you put this block into the cache, you can able to see that from the cache entry or the cache index, you can see only the lower order bits. So just by knowing the lower order bits, there are chances that the 4 blocks can place over here. They have a chance to be there. So among these 4 blocks, which block is residing, that to know about that, we should be aware of, we should know that will be known only through by using the higher order bits. So therefore, the cache also should maintain these higher order bits corresponds to the block that is present over there. Then with that, we'll come to know that whether the block requested or whether the word requested by the CPU, whether it's present in that cache or not. So that is known to be the tag bits and all. We'll see that the example clear to you. And along with these tag bits and the data, uh, and here there will be another bit, control bit that will be used, maintained by the cache. It's known to be valid bit and all. It's known to be valid bit. And this valid bit means, first of all, if a cache is there, and then first of all, whether the block is whether the cache is empty, or for a particular block, whether the particular entry is empty or not, to check that one, because initially the entire cache will be like empty. So in that case, there is no point in checking the tag bits or whatever and all. So first of all, there will be one control bit that indicates that actually whether the particular location, whatever you are checking for a block, whether the block is present or not. So for that, you can for checking that one, you have one single bit will be there. So with that bit, you can just check it out that whether the block is there or not. If the block, suppose for example, initially the entire cache will be empty. So at that time, all the valid bits will be 0. That means there is all the blocks will be 0. At that time, if the CPU references a particular entry, at that entry, just by checking the valid bit itself, you can say that the block is not present. It means that it declares as a miss and will fetch that particular one, right? So therefore, there are sometimes no that this is basically occurs during the initial point of a time, and where a particular entries they're not filled up, or they are like as and when required, then we'll fetch that block and we will make use of that. So therefore, to maintain that, to check that whether the block is actually, whether the entry in the block, whether it is valid or not, for that we make use of a 1 bit, whether 1 or 0. 1 indicates that there is a block, a physical block that is present there. But to check that in this physical block, whether is it the desired block or not, for that the tag bits will be used. For that the tag bits will be used. So first of all, whether check that whether any block is present or not in the given index, in the given cache index or cache entry, we will make use of this valid bit and all. So yeah, you can see the example, then it will be clear to you. Suppose, for example, we had taken the same example, whatever we had shown earlier, where the cache contained the 8 entries, and your main memory has the like 32 blocks, 32 entries. And here we'll assume that the block contains one word, only one word, and the block contains multiple words also. So this is initial state where the cache is empty, right? And that means that just you are starting the execution of a program. At that time, we don't know actually which blocks need to be required by the CPU and all, or which instructions are required, where the program starts, that you have no idea at all. So therefore, the cache will be empty. and the first initial reference and all. So therefore you can see that the cache will be like the valid bit will be no, like all will be like it will be zeros, like it is no. Like then afterwards the entire all entries are empty. Then when you start when the CPU start accessing the instructions one after another and all, then those instructions are first checked with the cache. If they are not there, then they are bring it back. That way the cache will be filled up. Yeah, this is the way you can say that. First of all, the cache CPU generates address of 22, for example, word address, and if the 22 is not available, then in that case, actually we'll find out this corresponding cache entry and valid. And if it is not there, then we'll bring that this one, the word from the main memory to the cache, and then we'll update the cache and all this way. You can say this is the way the cache will be updated. Here this 22 means here the lower order 3 bits, that if you perform a modulo, this will be your cache entry or cache index, right? 110. And then the value will be set because we brought that back here. That means there is a block, we are bringing one block here. And the tag of this block will be here maintained here 10, right? So so that way you can see the next one. There is some other one, so it's not available. So therefore we should bring it back and then we'll update. So likewise, these are the two entries corresponds to that. So likewise, you just these are the next three entries, and so that way the cache will be like as and when the CPU generates the addresses, it just updates. And sometimes no, it will suppose the 16 is entered, 16 was called, then the 3 was requested by CPU. So all the cases there are miss will be there. Then again the 16 will be called, for example, referred. At that time the entry is present already, so you can call it as hit. There the hit rises and immediately the data will be given to the CPU. So that way, and here this is the entry corresponds to the red marked one. Here we are requested for a word address 18, that is the physical address, and the corresponding thing in the cache will be like 010. This is the cache. When you perform modulo, you will get a lower 3 bits 010, but 010 already had some other entries there earlier. Already there is some other block is there. So, but this is a requested one, and as we know that here in this case here, so there are multiple blocks compete for only one location. So here in this case now this block 18 or word 18 is requested, but there is no space for that because already it was occupied. If you look at the previous one, already it was occupied with some other one. So now we have to replace that. We have to replace. That means we have to fetch this one. We have to override this at the same time. Whatever is there, that has to be again. If it is modified, then again it has to be write into memory, or it has to be. We have to replace this entry with the desired one. And so that way you can say this red entry is indicating that actually there is no space for that already. This particular entry, the cache has some block, but that is not the desired block. So therefore we have a miss rises. Then we will fetch that the desired block and we'll place it over here. So that way the cache will be updated. Sometimes if there are empty entries are there, then simply there is no issue at all. Just simply the requested data will be placed over there. And suppose already that entry was filled up with some other block, then we have to replace that. You need to replace that, right? So yeah, if you look at here, this is the overall the overview of the way the cache is organized, and cache will be the entries in the data, the whatever the address that is requested by CPU. So it will be accessed by using this particular mechanism. If you look at here, suppose for example, CPU generates a 32-bit address. Assume that your main memory is addressed with 32 bits. So therefore, these are the 32-bit address that generated by CPU. But the CPU first will contact the cache. First will contact the cache. So here, if we know that actually here the cache is organized like where the cache contains the blocks, where the block size equals to one word. The block may contain the multiple words also, but here just for the simplicity, we just assume that the block contains one word. Block consists of one word, right? But here the address generated by CPU will be, it's mostly the byte address, as we have seen already. The address will be like a byte address, right? And here where the cache deals with the blocks. Cache deals with the block. And here the block is nothing but one word. So therefore, here if you want to get a block address, the block address is nothing but here because the block contains one word, and here is actually byte address. So therefore, whatever the the byte address that is given. So from that byte address, if you divide by 4, you will get a block address, right? Because because it's actually byte address, but the block contains one word. It's nothing but 4 bytes. So therefore, if you divide by 4, you will get a block address. You will get a block. So the block address is nothing but here this the higher order 30 bits corresponds to a block address. The total 32 bits indicate the byte address. Out of that, the higher order 30 bits indicate the block address and all, right? Block address, or in this context, it's a word address also, word address. And now here, assuming that the cache size equals to, it can be able to accommodate 4 kilobytes. The cache size equals to, the cache size means usually it is referred with respect to the data. The cache can accommodate 4 kilobytes. It means 4 kilobytes means like 1 kilo words, or like 1,000 words, or like 1024 words, 1024, because word equals to 4 bytes and the size equals to 4 kilobytes. So therefore, it can able to accommodate 1024 words. 1024 words. That means 1024 blocks, right? 1024 blocks. So now from this 32-bit address, like we know that we'll get a block address by just removing the last two bits. The remaining 30 bits happens to be your block address. So this is the block address. Now, if you perform a modulo with the 1024, you will get the cache index. You will get the cache index, just similar to the previous one. If you look at it, if you try to see that. So there also you have a words, you have 32. We have a like the block size equals the block address equals to like 5 bits. 5 bits. Since there are 32 blocks are there, so there are 5 bits were there, and cache can accommodate only 3 bits. So therefore, if you perform 3 bits means there are 8 entries in the cache. So therefore, if you modulo 8 the block address, then you will get a cache entry or the location of a cache, the block location in the cache, within the cache. So that way here, here in this case, since the cache size equals to 4 kilobytes and there are nothing but 1,000 words. So therefore there are 1,000 entries in the cache. There are 1,000 entries in the cache. So these 1,000 entries in the cache can be designated or can be represented by 10 bits. Can be represented by these 10 bits and all. So once if we know the block address, right? Once if we know the block address, in that the lower order bits of a block address that indicates the cache index. Since the cache here, the size equals to like 4 kilobytes, nothing but 1,000 blocks. So therefore these 1,000 means, sorry, 1024 blocks. So these 1024 blocks can be accommodated with the 10 bits. So in a block address, the lower order 10 bits indicate the cache index and all, the cache index. That means the given address, this particular block is present in this particular entry. So that is indicated by these 10 bits and all. And this particular index at this particular cache entry, there are multiple blocks can compete. There are multiple blocks can compete. Here in case of 32-bit address, so there are remaining 20 bits are there. That means there are 2 power 20 blocks can compete for this location. So one of these 2 power 20 blocks can be present over here. One of these 2 power 20 blocks can present over here, right? As we have seen in the earlier very toy example, we have seen that there are 4 blocks can be placed in only one location in the cache. That's a very simple example where the block address equals to 5 bits and the cache index is 3 bits. Whereas here the block address is 30 bits, the cache index equals to 10 bits. The remaining 20 bits are nothing but the number of blocks where they can compete for a single location. So that's the reason here to know that whether the block that is present in the cache, whether it is a desired block or not. For checking that one, these higher order bits are required. Those are going to be tag bits. So therefore, the cache should maintain along with the data, the actual data block. It also should maintain the part of the address, that means higher bits of the block address has to be maintained, and that's known to be tag bits. And along with that, there is a 1-bit control field is required. See that whether the block location, whether the cache index actually contains the block or not, genuinely contain the block or not. So that is indicated by valid. So initially at the beginning, all valid bits are reset, all will be 0. That means the entire cache is empty, and afterwards whenever the cache entries are filled up, then this valid bit will be set accordingly. Valid bit will be set accordingly. So therefore here this is a valid bit and a tag bits and all. So when the CPU generates address to check that whether the the entry, whether the desired address instruction is available in the memory or not. For checking that one, we do this mechanism. First of all, from this address, we'll first find out the block address, and then from the block address, we'll try to find out fetch these lower order bits. How do you fetch this one? Perform a modulo with the cache size, right? When we perform modulo, you'll get this lower order 10 bits. So from this lower order 10 bits directly, because there is no need for maintaining the index here, because the cache is by default organized this way, like from lower address to the higher address. So therefore, these index bits are not, see, again, specifically it's not required at all, because the cache entries are such that this is the first entry will be 08, then 1, 2, 10, 23, like that. So these lower order bits, from these lower order bits directly will come to the cache. We can directly access this location. And here at this point of time, we should know that whether this entry, whether the block is present or not. If the block is present, desired block is present or not. For that, we'll make use of these two inputs. First of all, we had to check that whether the valid bit is present or not. If the valid bit is present, then that means there is some physical block is there. Some data was there. To check that whether data is correct or not. So from this, at that particular address, there are remaining 20 bits are there. These 20 bits will be taken here. And the tag that is associated to this particular block will be given as input to the equator comparator. If these two are equal, then it means that the requested block or the requested word from the CPU, it is available in the memory and all. It is available in the cache and all. So if this equality holds good, then it generates 1. And along with that, anyway, the valid bit also has to be set. So if both are 1, then the AND gate output will be 1 and it generates as a hit and all. If any one of them is not matches, or if any one of them is 0, then AND will generate as a miss and all. So whenever the AND generate hit at that time, the data will be passed to the CPU. So this is a simplistic case where the block contains only one word. So if the block may contains the multiple words also, like as we have seen earlier and all, as the block contains the multiple words, right? Multiple words, but the CPU requests only the one word only. It requests one word. It's not. It doesn't require the entire block and all. Because the address that is specified will be the byte address, and in that the CPU may want the word 32 bits out of that. So it means one word, but a block may contain the 4 words or 8 words or 16 words. So in that case, we require that here the tag whatever here. This tag, suppose if a block contains the 4 words, then the tag should maintain, or anyway, the tag corresponds to that particular block. Yeah, it doesn't matter, because even though it contains the 4 words also, the later we need to, by using this word offset, you can pick up the right word and then pass on to the cache. That I will just show you one. There is one. Yeah, here. Yeah, not here. Yeah, you can see here. You can see here the same thing, whatever I have shown here. Whereas here the block contains the 4 words. The block contains the 4 words, right? So in that case, but the CPU wants only one word out of this. So that will be decided based on this particular word offset. Here the word, that means here, as I mentioned, the block contains the 4 words. So therefore, to get a block address, what you need to do here, you need to divide by 16, because a word contains 4 bytes. And now the block is here assumed as 4 words. So therefore, the block size equals to 16 bytes. So because the byte address will be given. So to get a block address, you have to divide by 16 here. So therefore, you will get the block address, that is 28 bits you will get here. And then by using 8 bits, you will get the cache index. And then with that, you need to check with the tag, and also if the tag matches, then it means that whatever the word that is asked by the CPU, that is present here in this block. So, but it contains the 4 words. Out of these 4 words, it has to check which word is required. For that purpose, the word offset, whatever is here, the 2 bits here. So that will specify which word has to be selected, either 0001, 1011, whatever. So based on that, out of these 4 words, it will be because based on these 2 lines, it's kind of a multiplexer kind of a thing. So one of these 4 will be selected and it will be passed on to the CPU and all. Right. So that way, in case of if a block contains the multiple words, then we'll pick up the right word from the block and then pass on to this one. And the other part is remains same. Right. So this is known to be direct mapped cache, where the mapping mechanism is simpler. The mapping mechanism is simpler, where the multiple blocks will have only one location at the cache. And to know about that, among these blocks, whether the right block is present or not, for knowing that, we need to have some higher order bits are required. That's known to be tagged and all. So we have a cache means here the cache not only maintains the data, along with the data, some additional information also it maintains. One is the tag and the other one is the valid bit. So this is the total size of the cache. Among these, the data occupies this one, and the remaining are the meant for searching and accessing the cache and all. So we'll stop here and yeah, the next class, the Monday, I'm not going to take the class because I'm out of station. So our next class will be on Tuesday. So we'll start from Tuesday, wherever we stopped here. So far we just covered about memory hierarchy, and then one of the schemes of that, like direct memory cache, direct mapped cache, we looked into that. And there are several examples were there in this slides itself. Anyway, I'll make the slides available to you today. You can go through that. There are numerical examples. If you go through that, then you will get a more clarity, and whatever, if there are any gaps are there, that can be resolved. So we'll stop here, and our next class will be on Tuesday at 10 o'clock. So please make a note of this.